Stars are the engines that run the universe. Their life cycles create the heavier elements such as iron that make up the things around us. Therefore, it's very important to understand how stellar evolution works in order to understand how the universe works and how we came into existence.
The life cycle of a star begins when huge interstellar clouds of gas, mostly made up of hydrogen, contract under gravity. They continue to contract because there's no outward pressure, and this is because the gas molecules within do not collide with each other. This is when a protostar has formed. As the clouds continue to contract, the density of it continues to increase. Meanwhile, the core traps infrared radiation from dust, which has been heated by the collisions with the gas molecules within. Eventually, the outward pressure produced by the infrared radiation equals the inward gravitational force, and this is when hydrostatic equilibrium has been reached. When this is complete, we have the formation of a pre-main sequence star. The pre-main sequence star continues to contract while accreting matter onto its core. This causes the central temperature of it to rise, and eventually the temperature gets high enough to start hydrogen burning. When this happens, the main sequence star has formed.
Once the star depletes all its hydrogen fuel, fusion stops and core pressure falls. The outwards pressure due to nuclear fusion is reduced and is no longer able to support gravitational collapse. The core contracts, which causes the temperature of the core to rise. The heat released by the core heats up the exterior of the star until it becomes hot enough for fusion to take place. This results in hydrogen shell burning in a massive envelope. The star becomes a red giant. The buildup of helium increases core density until electron degeneracy. The core becomes incompressible. Its temperature will start to rise until about 100 million kelvins, where helium fusion becomes possible. It becomes a horizontal branch star. The luminosity starts falling, but temperature continues to rise. On a Hertzsprung-Russell diagram, it appears as if the star is moving back towards main sequence. Once helium is used up, the core collapses again. The star expands into asymptotic giant branch, with a carbon-oxygen core and helium-hydrogen shell burning. Low-mass stars are unable to fuse carbon. As fuel runs out, the core contracts again and goes through a period of superwind. The outer layers are blown off and ionizes the ejected atmosphere. It is now commonly known as a planetary nebula. Finally, the core cools down to become a white dwarf. The evolution path of mid-range stars is quite different. Type 2 supernova arise from evolved stars of 8 solar mass or above. These stars are able to fuse up to iron. In a contracting solar remnant with mass greater than the Chandrasekhar limit, electron degeneracy pressure can no longer withstand the gravitational force. The photodissociation of iron forms neutrons and emitting pulse of neutrinos. Under immense conditions, elements heavier than iron are produced by neutron capture. Core collapse is eventually halted by neutron degeneracy. This halt causes the outer layers to be rebounded, producing shock waves that blows off the rest of the star's materials. This is a supernova, and the total energy output can be as much as the energy produced by the Sun in its entire lifetime. Neutron degeneracy halts the collapse. The star is now a neutron star. During collapse, angular momentum and magnetic field strength is conserved. Thus, neutron stars rotate very rapidly and has very strong magnetic fields. To form a neutron star, the birth mass of the star has to be in the range of 8 to 25 solar mass. It will have a core remnant mass below the Tolman-Oppenheimer-Volkoff limit of 3 solar mass.
At this point, you may be wondering what happens to the large stars, the ones that have a birth mass of more than 25 solar masses. Well, they follow the same cycle as mid-range stars do. They also pass through a red giant phase, followed by a supernova, leaving a rapidly rotating neutron star. However, the life cycle of the largest stars doesn't end here. Until this point, the force of gravity is being overcome by degenerate neutron gas pressure. But for the largest stars, this pressure is not great enough to withstand gravity. Gravity wins in the end, causing the neutron star to collapse further. As a result, the volume of the star tends to zero, and we are left with an infinitely dense point, with a mass that is greater than 3 solar masses, which has such a strong gravitational pull that not even light can escape it. This is often referred to as a singularity. Singularities, or black holes, are formally defined as the object that is contained within the Schwarzschild radius. This is the radius at which the escape velocity is the speed of light. You may know this radius as the event horizon of a black hole. How do we know that these black holes exist when we can't see them? Well, the way we detect black holes is through the detection of X-ray radiation that it emits. As matter is pulled towards the black hole, it starts to form an accretion disk around it. The viscosity of the gases and matter in the accretion disk around the black hole causes the release of X-ray radiation. This is the radiation we can detect, so we can find the black holes. This is how the largest stars in the universe end their life.